Okay, here's that same problem we just did. First I solved it with a mechanics and materials approach. I did a little quickly, I'm assuming that's kind of review. If you need to, go back and look at your Hibbler book or whatever you use for mechanics and materials and review that. But that's one approach. And remember when we did the mechanics and materials approach, it has this sort of steps of figuring out the reaction forces and then the internal forces, using that to get the stresses, then getting the strain field using Hooke's law, and then integrating the strain field to get the displacement field. And this one's a little trickier because, in fact, to do the first step to get the internal forces, we need to also use the compatibility condition that the elongation of that bar is 0, because it's a statically indeterminate problem. The nice thing about the PDEs and the PDE approach and the finite element approach is it doesn't matter whether it's statically determinate or not. It's solved the same way. So that's actually a nice feature of it. And this one's actually a good example. I wish I could say I was clever enough to do it, figure it out from the start, but after doing it, it's kind of nice that the PDE approach, in a lot of respects, is easier than the statically determinate approach. So let's look at this problem with regard to solving the PDE. So to solve the PDE problem, like we did in class, we want to find this displacement field, u of x, on x on the range of 0 to L. Okay? We want to find x on this domain. Okay? Such that it satisfies the differential equation. Oops, I'm sorry. Should be able to write the right differential equation that would help. That's the differential equation. But now we have boundary conditions, okay? And in this case, the boundary conditions are two. That the displacement at x equal to 0 has to equal the displacement at x equal to L. And then they have to be equal to 0. It's fixed at both ends. Okay? All right. So we know that b of x in this case is just rho g. So let's substitute that into here. So I have u, the second derivative of u with respect to x. Let's put the little, this means second derivative, plus rho g on e equals 0, or the second derivative is equal to minus rho g on e. All right, this is a pretty easy one to look at. You can look at this and you can see that it has polynomial solutions. You could actually, the other way you can look at it, you can just integrate this twice. So if you integrate it once, you get the first derivative is minus rho g on e times x plus some constant of integration. And then if we integrate it again, I get u is equal to minus rho g on 2x squared c1x plus another constant of integration. Okay, we solve for the constants of integration using the boundary conditions. Anything of this form satisfies the ODE or the PDE. All right, and now we need to just invoke the boundary conditions. So u at 0, putting that into here, I just get C0, and that has to go to 0. So that tells me C0 equals 0. And then using that, we get it at x equal to L. It gives me minus rho g on 2 L squared plus C1 L has to equal 0. Or from that, I can see that C1 has to equal L rho g on 2. And that gives me, in general, the displacement field is going to be rho g on 2 L x minus L. Okay? Is that right? Oh, what am I doing? Sorry, guys. I'm plugging into the wrong one. Let's plug it into here. Let's be careful. Okay. So I've got u of x is minus rho g on 2x squared plus c1, which is rho g l on 2 times x plus 0. So now I can take out the rho, the g on 2. So let's take out rho g on 2. And that leaves me with L. Oh, I can take an x out as well. L minus x times x. And that's the displacement. It should match what I got before, but it doesn't. Did I make a mistake on this one? I think I made a mistake on doing this. I must have made a mistake on this. When I went back and did this, I did the integration. Here's chi. Oh yeah, I screwed up. Yeah. So this gives me an Lx. Yeah, I need to have an x in here. And then you can see this gives me rho g. I don't know why. There's x on here. I did. This x is the chi getting substituted for x. 2e and then L minus x squared on x. And you can again see this vanishes at x equal to 0, vanishes, and also at x equal to L, vanishes. Okay? So I get the same thing for the displacement. Displacement is equal, right? That's the exact solution, directly. Now, if you're going to do, that's fine. You notice the first thing we get is actually the displacement field. So you might want to go through and get the stress field, and that's a reasonable thing. But if we were doing finite elements, again, you would get a nodal discretization where you get an approximation for this displacement field that satisfies the boundary conditions and the PDE. That's what finite elements is doing. We're doing a little different approach. It's an approximate method. But the order in which we do things is actually still the same. You actually, remember we talked about finite elements being an interpolation. You can imagine this as being an expansion of some general interpolation, and that's what's going on. Okay. But then anyway, this is an exact solution. So if we do the exact solution, we got this, and then we can get the strain field. We know that the strain field is the derivative of the displacement field with respect to x. So when I take the derivative of that, I get minus rho gx plus rho gl on 2, which I can write as rho g L on 2 minus x. That's the strain field. And then the stress field would be Young's modulus times the strain field. Again, that's Hooke's law, but it's going the opposite direction. And that would give me rho g e L on 2 minus x. And that's the stress field. So you can see the stress and the strain fields are linear. Okay. They actually, if we were to plot it, let's plot. This is x. So at L on 2, it goes to 0. And it starts off positive, and it has a linear slope like this. This is the stress. This value here is going to be rho g e L on 2. Okay? Rho g e L on 2, negative. I think I did that all right. The strain I got over E. Why do I have over E? Oh, I dropped the E again. Ah, I'm such a bonehead sometimes. Where'd my E go? Ego, no joke. Right? Oh, I made another mistake. I'm sorry. Up here, this E became a... I lost the E here. I don't know why that fell out. So there should be an E here, E here, an E there, an E there. That puts an E here. That puts an E there. Now the units will work out better. That gets an E under here, and an E under here, and that puts an E under here. And that goes out when I multiply by E. So the strain is actually rho G on E, L on 2 minus X. The stress is rho G L on 2, as that form, and then the displacement, again, let's just get it right, rho G on 2E, L minus X times X. So the displacement has this quadratic form, vanishes at the ends, and then at the middle, where it's L on 2, I get L on 2 squared type of thing, so it actually looks like displacement looks like this. All right, so it stretches the most at the midpoint and then kind of quadratically tapers off to 0 at the ends. All right, and you can see that that gives me the same exact answers as I had when I did the mechanics and materials approach in the prior video, except what you can see is we went backwards here. We got the displacement, give or take a couple of dropped Young's moduli, got the strain, the internal stress, and then the forces. So it actually goes in the opposite direction. Okay? And actually, I think in this particular case, it's in some sense easier to solve the PDE than even the mechanics and materials approach. Okay? I hope, the errors that I did didn't really screw up the derivation. Okay?